Hello and welcome to Class 20, dealing with entropy, where we introduce the ideas of entropy and talk about reversible processes. This is the beginning of Chapter 6 in Borgnacki. Here's the objectives that we're trying to accomplish. I won't read through all of them, but basically we're dealing with the second law of thermodynamics as applied to processes, and we're going to introduce this idea, this principle, the increase of entropy, and we're going to try to calculate entropy changes, and basically we're going to try to get the idea across of entropy and how we use it in thermodynamics. So we want to define it first. Just like energy is an abstract concept, and so is entropy. It isn't necessarily, as I like to say, a real thing. It's a way that we try to describe how the world works from observation. So we created this thing called entropy. And so let's give it some definitions. All right, so there could be many definitions that will be presented, different concepts associated with entropy, but we're really talking about the ones that are going to be useful for us. And so entropy as a thing, we could think of it as disorder. It's a measure of disorder, but better for us, right? That might be more of a conceptual physics type of idea, but let's, in terms of thermodynamics, we'll say that it's irreversibilities. Irreversibilities. And spell check doesn't like that word, by the way. But irreversibilities, well, you can think of like we have reversibilities. There should be a V right there. We have reversibility. So like if we were to take a process, we already noticed that most of the time we can't have a perfect process, but we can have an imaginary perfect process that we can go in one direction and then we can go in the other direction, and we won't have had any changes between making this process. We recognize that's not actually possible, but we can simulate it or get close to it, like have a quasi reversible process. But because there's not possible to have reversibilities, we want to create this thing that we call entropy that we can use as a means of quantifying things. All right. So you can also think of entropy as thermal energy. So I'll take the time to write this down. Thermal energy unavailable. I like this definition a little bit better. To be converted to work. All right, so this gets really close in some respects to other definitions to like exergy, but for our purposes, this is a pretty good one. So these two will be good things to keep in mind. And I think the only way to get your head wrapped around what entropy is to start using it. But there are some conceptual things to talk about. So if we're going to assume that there are some reversible cycles that are possible and that they behave as shown, right, that we can go from step 1 to 2 right there, and that all of these are reversible cycles, right? So there's multiple ways to get from 1 to 2 is what we're assuming. And if it's reversible, then you can see that we can go backwards, right? So we can go from 1 to 2 by way of the path of A, right there. So if we go ahead and say, well, the heat change, right? This is the, by the way, going back from Chapter 5, recall from Chapter 5. We had the Clausius. Right? And this was the definition that we were using, right? We had this heat changed and divided by time. And we did a across the cycle, right? We integrated this small changes divided by the temperature through a process, and this temperature can change along with this, right? So this is a variable that's moving along, and we know that heat, its flow is a function of temperature, right? We need two different there can be very, very small changes in temperature, but there needs to be a change in temperature in order to have heat flow. So these are linked together. And when we go around a cycle, they have to equal 0, That's the definition of a reversible process. And so we could say that going from A to 1 to 2 from here, plus going from going from 2 to 1 right here, A and B, they equal to 0. And then we also use the principle, well, if these are reversible processes going from 1 to 2 and 2 to 1, then any type of reversible process, well, we can also say, by the way, that we're going to go from, instead we go to the path of C, right? We can go from 1 to 2 here by way of C, and then come back through B, and they have to be equal, they have to be, when added together, equal 0, right? By its definition. Then therefore, A and C have to also equal each other, right? Because this plus this, A plus B is equal to 0, C plus B is equal to 0, therefore A plus C is equal to 0. So let's read a little bit of this, but not word for word, maybe. We take that quantity right there is the same for all reversible processes from paths between 1 and 2. We conclude that this quantity is independent of the path and is a function of the states only. So it's a state function. We really like that, state functions, right? Because we can go, we can, once you find the information at a particular state, you can find all of the other states, all of the other quantities at that state. So that's a useful thing for us, right? So what we've just established is there exists this useful thing that we can have at a state, and we can find, once we found this and then another parameter, we can find all of the other parameters for a given state. Having a state function is a good thing. It is therefore a property, right? So this property is called entropy. It's designated S. It follows that entropy may be defined as the property for the substance in accordance with this relationship. So one of the really important things to us, repeating myself here, is we have defined a new property. That the property quantifies irreversibilities. And in doing so, we can now have something that we could use to define processes and finding a path from one point to another point. Not a path, excuse me. We could quantify what happens here by knowing something about the path that goes on in between the two things, if it is in a reversible path. Entropy is an extensive property. All right, so like if you chop this in half, if you chop the mass in half, this becomes half. So a lot of times it's better for us to do it entropy per unit mass, and that could be an intensive property, right? So we can have like the concentration of entropy in a particular mass. And then here's a good principle to understand. We will look at it further in different sections coming up. But entropy is of an isolated real system, right? So we're not talking about a flow here. We're just talking about a particular chunk of mass is always increasing. But we should recognize, though, that we do have influence in the outside world, so that we can have we can have a heat coming in, which will, in a sense, change that, have a quasi decreasing in a globally sense. All right, so that's always bothered me when I read this sentence, and I'm like, but when we take a look at a chart, we can see that we're going in the negative direction. So that doesn't mean that it always has to go from left to right on this TS diagram that we're about to introduce, but it does mean that as a whole, we're always creating entropy. And it's this right here, this idea right here, gives a process's direction, right? That it must occur in the direction of increasing entropy. And the only time that we don't have an increasing entropy is when we have this system here, where we have entropy hasn't changed. When we have zero change in entropy, that defines a reversible process. All right, so I don't know if I helped with any of that. And because it's a property, we could go ahead and we could, for a substance, we can come up with a chart, right? So here you go. If you have a pure substance, so I think this is, this is for steam, so water. We will find that we can create this find temperature versus entropy. And this is our TS diagram. And I would say it's a fair thing to state that there are two really important diagrams, and now we've introduced the second one. The first one was the PV diagram, the pressure versus volume diagram, and we use that a lot. So now we also want to use the TS diagram, temperature versus entropy. And for pure substances, they have a vapor dome, just like we were experiencing in some of our other graphs, because we had more than just the PV graph thus far. We've been drawing a vapor dome, but right here is our TS diagram. And this has a vapor dome, and it's useful to us to find the saturated liquid comes up to here, and the saturated vapor is down on that side, and we're going at a constant temperature when we're inside underneath the vapor dome as we're moving from saturated liquid to saturated vapor. And of course, where we are along here is going to be a function of the quality that we had, that X. So we have this equation that we've been used to, right? And you've probably seen it in the steam tables, that just like the specific volume, the internal energy per unit mass, the enthalpy, of course, per unit mass. Now we have the entropy per unit mass, and we can have this the quality of there will decide where we are along this path right here. We can also another important and useful diagram that we'll bring up is the enthalpy versus entropy. We don't quite use this as much as I used to as a younger engineer, because I would actually look things up on the enthalpy versus entropy on the actual physical diagram itself, because I dealt more with a lot. I went further in depth into steam plants because I was a marine engineer and we had a lot of steam plants back then. We don't really have as many now. But when trying to take bleed steam off of a turbine, we would need to extraction steam. We would want to know what the enthalpy of it was in a real plant, and we would take a curve that was pre-made. You might do something along those lines, but anyway, we actually use the physical enthalpy versus entropy diagram, and this actually has a name, the Moliere diagram. I've seen it used other times in other respects, that name, sometimes for other things that had enthalpy in them, but this is the primary one that you would associate there. And the vapor dome is a little harder to see because it's kind of stretched out right there, but it has a vapor dome. And you have to see lines of constant pressure. And if you were to once again, well, I haven't said it yet. One of the beautiful or very useful things in this diagram is we can go straight up and down and on this for an isentropic process. That is a process that is has constant entropy, right? And we'll see that's a useful thing. And the same thing here, true, is we could have an isentropic process straight up and down, but if there is some entropy, we can start to have an angle to it. And then at these different pressures right here, as we're extracting steam, we can find out what the enthalpy is of that. So that's sort of like one of the very useful things. And I think these diagrams right here, continuing on, notice these are TS diagrams. I think the two of them right here, they're trying to show you that, yeah, you might care about the a compressed liquid. This would be greatly exaggerated right here, that most of the time it's actually so close for a compressed liquid that for any compressed liquid you could actually just look up what the fluid entropy is, and because that really varies with temperature, it doesn't really vary with pressure, so even if it's a compressed liquid. So I'm 14 minutes in here, I'm going to start a new video. So this was a big kind of like introduction. I could have made this whole separate page into a different video, but I figured it was some stuff that you want to be exposed to, but not necessarily something that you have to have a whole separate video for. So I'll see you in the next one where we talk about the TS diagram with the Carnot cycle. coming back to you soon.